It's quite unfortunate that this class
This
was
call is
scheduled
now
to begin
taking
by
notes.
8:45,
This
but
call is now being
many of you are
recorded.
strolling in even now. This is like 15 minutes past time. I've been here since 8:43 waiting for you guys, and three of you have just joined the class. But that's fine. So about me, how do we define matter? You are the first person to join the class. How do we define matter? No response from her. So Christine, you can come to the rescue. What is matter? No response too. Matilda, what is matter?
Like 117. 0117.
Can you please mute yourself? Go to
Sir, what do you say?
what is matter? How do you define matter?
Okay, matter is anything that take up space and have mass.
Matter is anything that has mass and occupies space. So, and that's very correct. So, if we say wave nature of matter, what does that really mean? When we say wave nature of matter, what does that really mean?
I don't know that one, sir. I'm an art student, but I love all these physics. That's an
Okay, you're an art student, but you love being in physics class. Okay, that's interesting to know. All right, so just like you rightly said, matter is anything that has mass and occupies space. So when we say wave nature of matter, we are simply trying to talk about the fact that matter behaves like wave. All right. So wave nature of matter means that matter has a wave-like behavior. It exhibits properties as that of a wave. And every wave has properties. There are things that shows that, or there are things that depicts a wave. There are things that happens that we have to say that this thing is a wave. Example of such properties are, we have the reflection. Every wave does reflect. We have refraction. Every wave does refract. We have diffraction, interference, and polarization. So these are few properties of waves. And when we're talking about the wave nature of matter, we are trying to consider matter from that perspective of a wave, meaning that matter exhibits characteristics and properties of a wave, just like you can see on the screen right there. I found out that many a times trying to put down things on the screen, you guys usually don't follow up with the classes to the best of my knowledge. I don't know, the responses usually you people give are always very weak, not encouraging at all. So I have to come up with a written note. I think that might help. So some of you that may want to write down things, you like writing down notes, I think I've been able to put down stuffs enough for you to take your time and write it down and read. Okay, so even if you don't want to write notes in this class, just listen and look at the examples that will be solved and how they are being solved, and take note of the equation. So everything is written down clearly, so you can always go back and do the writing yourself at your own time. So just like I've explained the few properties of wave, so examples of these particles, examples of the particle, this, remember when we talk about matter, anything that has mass. So anytime we talk about matter, it means that the thing we are talking about must have mass. It means clearly from what we have here, that electron, of course, electron has mass. Electron is a matter because it has mass. X-ray, X-ray is a matter because it has mass. Photons is also a matter because it has mass. So we can actually compute the masses of these particles. And scientifically, we know how to find the mass of an electron, the mass of a photon. So all these things are matters. All right. And these are few examples of matters, or few examples of particles that have these wave-like behaviors: the electrons, X-rays, and photon. All right. So de Broglie was the first scientist that gave us the relationship, or that gives us the energy, the relationship between the energy and wavelength of these particles. He was the one that gave us that relationship between the energy and wavelength of such particles. And that is what I try to explain in that paragraph there. So he suggested that high energy behaves like a wave because, let's go back, because it exhibits every wave properties. Now he gave us the relationship between the wavelength and the momentum of those particles. And that is what I try to block out here by this equation. So this equation shows us the relationship between the wavelength of a particle and the momentum of that particle. Clearly, so it means that according to this formula, we can actually compute the wavelength of a particle using the formula that lambda equals h all over p, where p is the momentum and h is a Planck's constant. And this Planck's constant has a value, and the value is actually 6.63 times 10 to the minus 34 joules second. And that is the value of your Planck's constant. As the class proceeds, even when we solve problems, you'll be seeing the applications of the Planck's constant. So take note that according to de Broglie, that the relationship between the wavelength of a particle and the momentum of that particle is given by lambda equals h all over p, where p is the momentum. And of course, if I try to substitute the value of p, remember momentum is simply mass times velocity. So if I try to substitute p with mv, which is mass times velocity, I'll be having that the lambda, which is the wavelength of the particle, is given as h all over mv. So this thing here, this equation here is called de Broglie's wavelength. So anytime you hear de Broglie's wavelength, don't forget that according to de Broglie, that the wavelength of this particle is given by h over p. So it is called de Broglie's wavelength, or lambda equals h all over mv. They are basically saying the same thing. So it all depends on what you're given and what you need to do. So if you know the momentum, simply divide the Planck's constant by the momentum. That gives you the wavelength of that particle. But if you don't know the momentum, but you know the mass and you know the speed, for example, let's say such a thing as a photon, all right? Or let's say an electron. Of course, electron travels with the speed of light. So electron travels with the speed of light. If I want to find the wavelength in which this electron travels, all I'm going to do would be to the wavelength lambda becomes Planck's constant h all over what the mass of the electron multiply the speed of light. You see that? So if I divide the Planck's constant by the product of this mass and the speed, that would give us the wavelength of that very particle. And that is what this whole note here is all about. All right? Are you with me? I'm sure you can hear me, right? Okay, as usual. All right. So that is that for that formula there. So that formula there is called the de Broglie's wavelength. Okay. And now this other slide here, what I try to do here is to try to bring a relationship between the de Broglie's wavelength and the Einstein's energy equation. All right. The Einstein's energy equation. I try to see how to create a relationship between the Einstein's energy equation and the de Broglie's wavelength. You see that? So what does the Einstein's energy equation talk about? According to Einstein, the energy equation is given as E equals hf. So this is what the Einstein's energy equation is all about. That E is equal to hf. All right, where E is the energy of the photon, and of course h is Planck's constant, and then the f is the frequency with which the wave navigates. All right.
Good evening, all.
Okay, please, I'm sorry. Can everyone hear me?
Yes, sir.
Oh, my network logged me out, so I was trying to fix it. I'm sorry for that. So, what was I trying to explain? I think I was trying to explain the de Broglie's wavelengths. Yes, okay, we're done with this. Okay, I think this is where we are. Right. Yes. Okay, so just like I said, for those of you that just joined, I can see many more persons have joined the class. So I said, according to de Broglie, that the relationship between the wavelength of a particle and the momentum of that particle is given by the de Broglie's equation, which simply says that lambda, which is wavelength, equals the Planck's constant all over the mass times v, where the mv is actually the value for the what, for the momentum. Look at the question here. So lambda equals h all over p. If p is mv, so we have that lambda equals h all over mv. So this is how we calculate the wavelength of a particle. Remember, we are discussing the behavior of the wave nature of matter. And we started by saying that matter, wave nature of matter implies that every matter has wave-like properties, all right? So matter have wave-like properties. Remember that matter is anything that has mass and occupies space, all right? So that means that even you as a person, you have wave-like properties. So we can calculate the wavelength, your wavelength as you are right there. The only thing is that the more massive the object is, the more massive the object is, the smaller the wavelength. The wavelength becomes small. So you can see from that formula, according to de Broglie, from this formula here, if lambda equals h all over mv, it means that if m increases, so if the mass is increasing, then lambda is going to become smaller. So the more the mass, the less the wavelength. So which is the reason why, even though matters behave like a wave, but a matter that has a greater mass will have almost insignificant wave properties, all right? Because the wavelength is going to be small. But the idea is that every matter behaves like both wave and particle. And now Einstein began to give us the relationship between the energy of this particle, and also the relationship between the energy of the particle and the frequency, the wavelength, as the case may be. So now you can see from this equation that the energy of a particle, according to Einstein, the energy of a wave particle is given by this equation here, that E is equals to mc raised to power 2, or mc squared, all right? So this is actually the energy of a particle according to Einstein, where m is the mass of a particle, and then c is the speed of light. So for instance, if I want to calculate the energy of a photon, all right? So what I need to do here is simply to multiply the mass of that photon and then by the square of the speed of light. And of course, you know, speed of light is a constant value, which is 300 million meters per second, or 3 times 10 raised to the power 8 meters per second. So if you multiply that by the mass of that particle, that gives you the energy of that very photon. I don't know if it makes sense. So the energy of a wave can be given by this equation also according to Einstein. So if E equals mc squared, and also E is equals h times f, which is the Planck's constant, which is h, multiplied by the frequency of that wave, which is what? F. All right. It means that we can actually equate the two equations together. So if I equate this equation with this, I'll be having this equation right here. That's what I did here. So if I equate equation 1 and 2, it means that mc squared is equal to what? hf. And from here, I can choose to make f subject formula. It means that the frequency of the wave is given by the product of the mass and the square of the speed of light divided by its Planck's constant. All right. So this is how we got this formula here. So just in case you try to find the frequency of a wave particle and you already know the mass of that wave, the mass of that particle. So what you need to do, simply multiply the mass by the square of the speed of light and divide by the Planck's constant. That would give you the frequency of that very wave particle. That is what we did here. All right. But now recall from your elementary physics, we have that V is equal to F lambda. So if V is F lambda, it then means that frequency can be written as what? V all over what? Lambda. Is that correct? Yes. So if I try to make F subject formula, F becomes V all over lambda. Where this V is equal to the speed of light, it means that we can write it as C all over lambda, because C there is simplify the velocity of that light, or the speed of the wave of light, which is the speed of a photon. All right. So it means that if I substitute C all over lambda back into this equation, I can actually get back my de Broglie's equation, or de Broglie's wavelength. So if I choose to put back this equation right here, if I put this thing, substitute it into this equation right here, it means that I'll be having that V all over lambda is equal to what? mc square all over h. From here, I'll be having that V all over lambda is equal to mc square all over what? H. All right. But from here, I can choose to make lambda subject formula. And of course, if I make lambda subject formula, I'll be having that HV all over mc square is equal to lambda. That's exactly what I have here. HV all over mc square is equal to lambda. Remember, the C there is actually the velocity of the speed of light. So that's why you are seeing C in this my very equation. All right. So other than V, you see C, because I consider the C to be the speed of light, which is the velocity of what? Of a wave particle in this case. All right. So lambda is equal to HC all over mc square. And of course, the C cancel out one of the C. I'll be having that H. Lambda is equal to H all over mc. That's what I have here. So if lambda equals H all over mc, remember the mc, the C there talks about wave. That brings us back to our what? To our de Broglie's wavelength, which is that lambda is equal to H all over what? mv. All right. But there is another form, even though I didn't put that here, but we're going to solve a question involving that. This de Broglie's wavelength can also take other forms. For example, let's try to make this substitution right here before we solve a question. Let me go straight to a slide. Remember, we are discussing that lambda, if we say that lambda is equal to m to h all over mv, it implies, recall that kinetic energy Ke is equals to mv squared. Sorry, 1 over 2 mv squared. It simply means that if I want to make V subject from right here, if I make V subject from here, I can have that. First of all, let me multiply both sides by 2. I have that 2 Ke is going to be equal to mv squared. All right, so the 2 cancel out the half on the right. So I have that 2Ke equals mv squared. So if I divide both sides by m, I'll be having that V squared is going to be equal to 2Ke all over m. All right. So from here, of course, if I take the square root of both sides such that I'm going to get what V would be, it means that V becomes 2 square roots of 2Ke all over n. So I can make this substitution right here. I can take this V, the value of V, and put it back into this de Broglie's wavelength. So let's call it star. So if I substitute V as square root of 2Ke all over m, it means that I'll be having that. This implies that my lambda, which is my de Broglie's wavelength, is equal to what? H all over, remember it's mv, so it's going to be m square roots of what? 2Ke all over n. So where that is the value of my V. But this doesn't make sense leaving this like this. I can bring this m into the square root, but if for me to do that, it's going to take up a power 2. Remember, if I write this like this equation can simply be written in this form, that h all over, let's say, m square roots, then I'll have square root here of 2ke all over m. Now, what I simply did by this is because this square root can cancel out the square, I get back this value right here. So I want to bring the m into the equation back. Remember, these two things are multiplying. So according to the law of what? Surd. If you have two solid numbers multiplying this way, so they can share one square root. So it means that I can write this equation as lambda equals h all over square root of what? M square multiplying 2ke all over m. Remember, both this m, everything is inside my square root. So please let me elongate it a little. So take note, everything there is inside the square root. And clearly, m, cancel out one of the m here. I'll be having another equation that lambda is equal to h all over 2 square root of 2 So this is another equation. Now, this equation is only applied. Now, if you take time and look at what I did, you'll realize how this equation here was being obtained. So if I know the kinetic energy of that very particle, and that's the energy with which it moves, and then I know the mass of the particle, I can simply compute the wavelength lambda by dividing the Planck's constant h by the square root of the kinetic energy multiplied by the mass, then multiplied by 2. That's exactly what this whole equation is all about. So in physics, we can always make substitutions. These things are not difficult, but if you can take note of how the substitutions are being made, it makes the whole thing easier. So you might not have I think I've seen a question. Maybe I added it to my notes here. I don't know. We'll try to check. I saw a question where they asked us to prove this thing I just did now in one of the past WAEC problems. All right. But whether you're being asked to prove it or not, that doesn't change anything. The whole thing I want you to get is that this wavelength can be computed with this formula. Take note that the wavelength of a wave particle is given by this equation, provided the kinetic energy of that wave particle is known and the mass of that particle is equally known. So I can calculate the wavelength of that very particle. All right. Also, if I'm not being given, but I know the momentum, or I know the mass and the speed, so I can also use this. But if the mass and the speed is not known, but I know the momentum, it means that I can say that lambda becomes h all over p, because p is the momentum of the wave particle. All right. So if I know the momentum, I can divide the Planck's constant by the momentum, and then I get the wavelength. But if I know the mass and the speed of that wave particle, I can divide the Planck's constant by the mass and the speed of that wave particle, I get the wavelength. Also, if I know the kinetic energy and I know the mass, I can equally apply this equation, and that gives me the wavelength of that very particle. And that is what this 3 equation is all about. So take note of that. But if you are asked to calculate the energy of that wave particle, the energy of the wave particle can be computed by this Einstein's wave equation. If you know the mass, if you know the frequency of the wave, it means that the energy of that very wave particle is given by h times f. Where the f there talks about the frequency, and then, of course, h is the Planck's constant. But if you don't know f, how then will I find energy? Let me show you that, because these equations many times can be related. I said that the energy of a wave is given by what? hf. So the energy of a wave particle is given by this equation. But you know that what? V is equals to f lambda. It means that if I make f subject, I'll be having that f becomes v all over lambda. So this implies that the energy of a wave particle can also be calculated by multiplying the Planck's constant by the speed divided by the wavelength. All right? Because f is actually v all over lambda. If I make that substitution, that gives me the energy of also that wave particle. So if I know the speed and I know the wavelength of the wave particle, I can calculate the energy of that particle by simply multiplying the Planck's constant by the speed and then divide it by the wavelength of that very particle. That gives us the energy. So you have to be careful to know when to make your substitutions. You have to be careful to know the equations to use. You have to be careful to know what to do at every instant in time. So I don't want to bug us with so many things, because on this aspect of physics, all you need to understand is how to use your equations and understand the question also, just like you'll see us do in the example. So let's look at this example right here. Now, this example here says, what is the wavelength of an electron moving at the speed 10 raised to power 8 meters per second if the mass of the electron is 1 times 10 to the 30 kilogram? And then they gave us that the charge of the electron is 1.6 times 10 raised to power minus 19 coulombs. They gave us that the speed of light is 8 times 10 raised to power, that's 3 times 10 raised to power 8 meters per second. And then the Planck's constant, of course, is 6.6 times 10 raised to the power minus 34 joules. So even though that is cut out, so you can take note of it. This Planck's constant, H, the value is H equals 6.6 times 10 raised to the power minus 34 joules second, please. That's minus 34. Minus 34 joule second. So that's the value of Planck's constant H. So this question says we should find the wavelength of the electron. So how are we going to do this right now? What do we do? So, and I want someone to respond before we can do it together. Even though I'm used to the fact that you guys don't respond in your classes, but I still want to give the benefit of doubt. So who knows what we are going to do here? What do we do in this very equation? In this very question, to compute the wavelength of that electron moving with that speed. I don't want to call names, I just want someone to respond. Everywhere has gone mute. Let's believe that someone is thinking.
I just try to reduce it like a bit. I think 1 inch or so. Those people might feel it's too long. And some the last 2 girls get, I wrote that one, I've done the that one, they're wearing 16. So there's something for me feel like it's a big shirt. But still I can't still tell because I don't know if this is
Does it mean nobody has an idea of what we're going to do?
It's not as though it's bad, but it's short. You understand? But I can't still tell. I can't talk about the heights or those things. Only they are short or they are short. You understand? So if they're not
Okay, maybe I will have to comment right now, because if no one is saying anything, one talking, but you guys always makes it look like that's the way a class should be. Okay, let's begin from the new person in our midst. Efosa, this is the first time I'm seeing you, right? I think this is the first time I'm noticing your presence in the
Yes,
class.
sir.
Okay,
Yes.
so Efosa, what do we do? How do we calculate the wavelength of that electron?
Yes.
No response from Efosa. Lucas, how do we calculate the wavelength of that electron?
Sir, my network was shaking, so I don't understand.
What don't you understand, Efosa?
From the starting.
You didn't understand from the starting.
Yes. I guess as we start with the examples, I will understand.
I should do what?
I guess as we start with the examples, I will understand.
You understand. Okay. Basically, let me run through again in the next 2 minutes before we answer that question. All right. This, everything I'm saying so far, maybe I'm not going to use, let me try to use my Now, we are talking about wave nature of matter, and we said that matter behaves like a wave. And what we mean by that is that matter has wave properties. What are the properties of a wave? What are the properties of wave? Refraction, reflection, diffraction, interference, polarization. So basically, we are trying to say that matter has these properties of wave. And now, if matter has the properties of wave, examples of such particles are the electrons, your X-rays, the photons, and the lights. So these are particles that behaves like a wave. Remember, what is matter? Matter is anything that has mass and occupies space. So before we can say that something is matter, it means that thing has mass. So electron has mass, hence electron is matter because it has mass. We have such a thing as the mass of an electron. And according to de Broglie, he gave us the wavelength of a wave particle, the wavelength of a particle that behaves like a wave. And he said the wavelength of a wave particle can be calculated by lambda equals h all over p, where p is the momentum of that particle. All right. Okay, but you know that momentum can be defined in terms of mass times velocity. It means that lambda is equals to h all over mv, where mv is the momentum, mass times velocity. So this equation is called de Broglie's wavelength. De Broglie's wavelength. But according to Einstein, Einstein gave us that the energy of a photon is given by E equals mc squared. I want to prove back this equation to you. Okay, E is equals to mc squared, and also the energy of a wave is equals to what? hf. So this is the energy of a wave, and this is the energy of a wave particle. So since particles behaves like wave, it means I can actually equate these two. I can actually equate equation 1 and 2 together. If I do so, I'll be having that hf is equal to mc squared. All right, hf equals mc squared. And if I try to make f subject formula, I'll be having that f is equals to mc squared all over lambda, which is the wavelength. So this is the frequency of a wave particle. So if you want to find the frequency with which a wave particle oscillates, it means that I can do multiply the mass by the square of the speed of light divide by the wavelength. That gives me the frequency. But remember that I want to prove what is it called now? I want to prove this de Broglie's wavelength. That's exactly, sorry, this is not lambda, this is h, Planck's constant. But I want to prove de Broglie's wavelength. So it means that, recall that we say that V is equals to what? F lambda. This is your basic wave equation, relationship between the speed, frequency, and wavelength of a wave particle. So V is equals to F lambda. Of course, it means that C is also F lambda, where C is the velocity or the speed of light. So if I try to make F lambda subject, if I try to make F subject, my F becomes C all over lambda. So I can substitute C all over lambda by this very equation. So I have that F, which is C all over lambda, becomes mc squared all over h. And clearly from here,
Sorry, sir.
yeah,
Your screen is not showing no.
my screen is not showing. For how long now?
I thought it was my network. That's why I left and came back, but it's not showing. I don't know.
You guys can be powerful. Oh. You guys are powerful people. My screen are not showing, and some persons are just there listening to audio. Oh dear God.
The only thing I will do,
Okay.
tomorrow morning or so, I'll make a video and I'll explain what I mean by that. So anybody that feels it's a very free space, someone that feels that you are
Okay.
tired.
So C, if I try to make this substitution, so C all over lambda is equals to mc squared all over h. And clearly, if this is true, it means that lambda all over C is equals to h all over mc squared. Of course, I can cancel out C from both sides. It means that lambda alone is equals to h all over mc. where C is equals to V, I'm going to get back this de Broglie's wavelength, that lambda is equals to H all over mv, this equation right here. And the next I did was to show us relationship between kinetic energy and the wavelength of a wave particle. But that would be a total different. I don't want to do that right now again. Maybe when I see a question. So you can always go back and check what we did to see how we derive this very equation. That lambda is equal to H all over square root of 2ke multiplied by the mass of that wave particle. But this equation we're trying to solve right here. The question says we should find the wavelength of an electron moving at a speed of 10 raised to the power 8 meters per second if the mass of the electron is 1 times 10 to the 30 kilograms and the charge E is 1.6 times 10 raised to the power minus 19 coulombs. The speed of light C is 3 times 10 raised to the power 8 meters per second. And then they gave you your Planck's constant, which I wrote out there to be 6.6 times 10 to the minus 34 joules second. So the question simply says we should find the wavelength. I don't need to use every value given to me because clearly I know that lambda is simply what? H all over mc or mv. So lambda is H all over mv. And since I know the value of H, I know the mass of that electron, and I also know the speed, which is the speed given clearly here, the speed of light. It means that I can find, of course, electrons navigate with the speed of light. All right. So it means that lambda, I can write this equation here as lambda equals H all over mc. So the wavelength lambda is equal to Planck's constant, which is 6. Fast. No need. Put it, somebody should do this for me. So put in the values. Lambda is equal to H all over mc. Plug in the value. This is your age here. Your age is 6.6 times 10 to the minus 34. Your mass is clearly given to you right here as, where is it? 1 times 10 raised to the power 30 kilograms. And then the C is given to us as 3 times 10 raised to the power 8 meters per second. So someone should put in this value here and find the wavelength of that wave. So I'm waiting to hear your response.
Government roundabout. That bank to bank. Do you want to use riders difficult? If I'm using bus driver, you want to just if you say water or something like that. For if you want to use rider can be more specific about your location. I never finish.
Is someone trying to solve the equation out?
I'm coming.
Okay.
The answer is 2.2 times 10 raised to power minus 72.
The answer is what? The answer is what?
10 raised to power minus 72.
Does anyone agree with that? Remember to put the Planck's constant is already given at 6.6 times 10 to the minus 34 joule-second. The mass of the electron was given to us as 1 times 10 to the... Oh, please, the speed of the electron was also given. See that? So we are going to use the speed of the electron. So the speed of the electron was given as 10 raised to power 8, right? That was what they gave us there. 10 raised to power 8. So it means that this value here is going to be V. So we are actually working with this equation. Don't use 3 times 10 raised to power 8. Just use 10 raised to power 8, which is the speed with which the electron is moving. So 10 raised to power 8 meters per second. So multiply the mass by the speed and then divide the Planck's constant by that product. And that gives us the wavelength. So I don't know whether that was what you did, Obawomi, right?
Yes.
Okay. All right. So let's move on with the question. So what is the energy? Okay, I even solved the question right here. The solution to that question, look at it right here. I didn't know it was included here because as my student, this was the note I used in class while I taught. So this is lambda equals H over P. Of course, everything just like we stated it, we have the Planck's constant, which is this, divide by, multiply by the mass and then the speed. Everything will give us this value from what? So you should get something, you should get this value here if you actually put in those values correctly. This should be the value you get as the wavelength of that very electron. Now, the question B says, what is the energy of an electron with a wavelength of 10 raised to the power minus 10, minus 10? Is that minus 10 or minus 12? Minus 12 meters. So they're trying to ask us to find the energy of that very electron. So how do we find energy of electron? Simply put that E, remember, E is equals to what? HF. But F wasn't given, but we were given the speed. We're given the speed of light here, and we are given also the wavelength. So we know the wavelength. So we can actually do that E is equals to H. Remember, F is simply V all over what? Lambda. So it means that I can put in the value of V and lambda alongside the Planck's constant. If I do that, if I do exactly what that formula says, that would give me the energy of the electron moving with that wavelength. So that is exactly what is being done here. So the question says we should find the energy of an electron with a wavelength of 10 raised to the power minus 12 meters. You see, nothing else was given. All I was given was just the wavelength. So it means that I'm going to use this relationship to find it. And that's exactly what was done in this solution. And I got the value to be what? 5.2. Oh my goodness, that should be 5.28 times 10 to the minus 13. Of course, the unit for energy is joules, right? That's the unit for energy. Joules, joules. That's it. So you can do well to try that out. So that was exactly what was done there for us to find the energy of that very electron. So this concept is very easy. In fact, this aspect of physics, all you need to know is just relationship and formulas, all right? So once you can always know the relationship, the formulas, every other thing becomes easy. And you have to know what you ask to find and how to make the subject at every instant in time. Because sometimes the equation doesn't really appear in the form in which you know them. So it's still the same formula, but you just need to make a little substitutions for you to achieve the results you are looking for. Now, there's a question they gave us right here. The question, I didn't look at this question. This is a typical WIEC question, and they said an electron of mass with charge E moves through a potential difference and a speed of V. showed that the Broglie wavelength associated with electron is given by this. Okay, even though that question wasn't copied correctly, but I could get what the student is trying to write out here. So they are trying to ask us to find that we should show that the de Broglie wavelength, remember the Broglie wavelength is that H lambda is equals to H all over what? P. So they want to, they are asking us to show that this relationship here is equal to this relationship here. And that was what I did before the class, even before I started solving question. And I want to believe you understood it. Any need to do that again? Okay, no need. You understood it, everyone. I want to believe that up to the point I proved this relationship, everyone understood it. Please, I need responses. I need responses from you guys to move on with this class.
Yes, sir.
Only one
Is it
person
like
responded.
Yes, sir.
A voice of one is your voice of
yes,
ten.
so
I
Yes,
didn't hear
sir.
you.
Sir. Yes, sir.
Okay. All right. So let's try to take further questions. Let's try to take further questions. Just hold on a bit. Okay. I still want to believe you all can see my screen right here, right?
Yes, sir.
Okay. The reason why I'm putting on the notes is so that anyone that feels he or she wants to make a note of what is being said, these are detailed notes that I use in a physical class I had with your colleagues also. So I just need to bring up the notes to this class. So it doesn't look like we are doing difficult things. See. Oh my God. Okay. Actually, I wanted us to see another question, but I could see that I think I only did one question, and I think that's enough for us to understand the usage of that formula. But there's another heading I want us to look at, which is also very important. The one we did is seeing the relationship between how we can compute the wavelength of a wave particle. You've also seen how we can show the relationship between the kinetic energy of that wave particle and the wavelength, the de Broglie's wavelengths, as the case may be. You've seen how we did that. And this one now is talking about energy quantization. I'm trying to see how the arrangement of this note is. Energy quantization. How many of you have heard about energy quantization, if I may ask? Has anyone here heard about energy quantization? I know you've heard about it,
Yes, sir.
even though you may. Okay. So when we say energy is quantized, what does that really mean? When we talk about energy being quantized, what does that mean? In your own understanding, Bawumi, okay. Because of time, let me just go straight. And when we talk about energy quantization, we are trying to talk about energy, um the ability for particles to gain energy. All right. So once a particle, let's say an electron, a photon gets energy, they move from one energy level to another energy level. So we can say that that particle has been quantized. All right. So the energy of electrons consists of small unit of packets that is called quantum. So anytime we have these particles begins to get energy so that they leap from one energy level to another energy level, we say that there has quantization or energy quantization has taken place. And of course, this subtopic still builds up from what we did right here. That is why you see that the relationship always, the energy of a particle is given by this equation here, that E is equals to HF. Of course, you know what every parameter there talks about. And that is what we are trying to explain in this very thing. So the ability of this electron to gain energy, to jump from one energy level to another, is what we mean by energy quantization. That is all the quantization theorem, and that is what it's talking about. So an electron and a particle gets energy, and then it moves from one energy level to another energy level. Imagine yourself, you are here. Let's say I have this more like energy level. All right. So somebody, you are standing here, another person is standing here. The ability for you to move from here to a higher energy level, for you to do that, we say that you as a particle here, you've been quantized. And that is what the quantization of energy is talking about. And now the next thing we have there is the energy level of hydrogen, because hydrogen particles is a very, share my screen. You can see my screen. Please, does it mean everyone can see my screen, or it's just you that can see my screen?
No,
Okay, several other person can see my screen. So please, if you can see my screen,
I can
then
see
it
your
means you may
screen.
just log out and log back again. Let's see, it might be your network. Okay, you can. All right. So let's move on. So the energy level of hydrogen can be calculated by this equation, that E is equals to En minus E naught. En minus E naught, where this E here is talking, of course, we mean that En talks about the energy of that particle when it's being excited. All right. So when the particle becomes excited, the energy level it attains is what we mean by En. So this is the excited energy state of that particle, where this E naught is the ground state. So when there is no excitement, the electron or the particle assumes a ground state energy level. All right. So, but once there is an excitement, that particle is going to jump from that ground state to a higher order energy level based on what the excitement is. So it can be the energy, it can be the excited state 1 or state 2, state 3, as the case may be. So the excitement in that particle determine what the state of the particle, energy state of that particle will be. So anytime you're being asked to calculate the energy difference, all right, you're being asked to find the energy difference between a particle as to be from where the particle was to where it is. You just subtract the current state from the initial state. In this case, the initial was the ground state energy, and now the current state can be En. This En can be E1, and they will give you the energy level of where that electron is. And for hydrogen, the ground state electron has a constant value. It has a constant value, and that is what is being captured. I'm trying to see, how did I mix up? It has a constant value. Look at it right here. The ground state energy is the lowest state energy in an atom. And of course, for a hydrogen, it has a constant value, which is minus 13.6 electron volts. So this is the value of the ground state energy of a hydrogen particle, of a hydrogen atom. All right. So this energy level is the ground state energy. That's your E naught. So once we are talking about hydrogen particle, the E naught has this value. And of course, from what we did when I taught you about, I think that was was it photoelectric effect or one of those topics? We saw how we converted from electron volts to joules, and we said anytime you have to convert from electron volt to joule, you simply multiply that value by the charge of an electron, which is 1.602 times 10 to the minus 19 coulombs. So if you multiply this value right here by 1.602 times 10 to the minus 19 coulombs, we are going to get the value of this ground state electron in joules. All right, that's what this whole thing here talks about. And then, how then do I find the En? If I know the ground state energy level, how then do I find the En? Because if the En is not given, they can tell me that the En, I should find the energy difference for a hydrogen particle if N is equals to 2, or if N is equals to 3, or if N is equals to 4. So how would you find the En? For you to know the energy difference, you need to know the En. And the En has this general formula right here. This is it here. So anytime the energy level of that particle is not given, you want to find it, all right? So what you're simply going to do is to substitute, use this formula to find the energy level, the excitement state of that energy based on the level that will be given to you. So if N equals to 1, you're going to put E1 becomes 13.6 EV all over 1 square, all right? So if En equals to 2, of course, 13.6 EV all over 2 squared, just like that. If N equals to 3, that is how you keep on doing it until you find the energy level of that very particle. All right. So if you want to find the energy difference, then you subtract this, you subtract the ground state electron from this very one here. So let's say I want to find the energy difference for a particle at N equals to 2. From what I did here, you already see that my E2 is equals to 3.4 electron volt. So it means that the energy difference is going to be what? E2 minus E naught, which is what? 3.4 EV minus, this is minus minus. You see that? Because E naught is minus 13.6 electron volt. So I'm going to have double minus. Let me keep this on landscape. Forgot to do that. So I'll be having double minus here. So this means that I'll be having 3.4 EV minus minus, I have 13.6 electron volt. Of course, double minus will give us a plus. This becomes 3.4 plus 13.6 electron volt. And if I add up everything here, that is going to give me the energy difference of that electron of that particle at n equals to 2. So that is it. So if you are being given the what is it called now, the ground state energy, you can always find what the excitement is at every level, whether 1, 2, 3, or 4, as the case may be. So take note of this formula. It's very, very important. Now, there is a relationship I proved here, which is the equation of energy radiation. So we remember from what we said before that E is equals to what? HF. And also, I said for the energy quantization that the energy of the particle, when it becomes quantized, the energy can be found by what? Subtracting the excitement state energy, subtracting the ground state energy from the excitement state energy. That's this energy right here. So if you do En minus E naught, where N can be any number, 1, 2, 3, 4, as the case may be, we are going to find the energy difference, which is the energy at the energy difference, which is the energy of that particle when it becomes excited. All right. So if E is equals to HF and E is equals to En minus E naught, I can equate equation 1 and 2. And if I equate them, I'm going to have this, that HF equals En minus E naught. Of course, if I try to make F, if I try to substitute F as V all over lambda, I'm going to get this equation right here. All right. So of course, if I replace C with V, where C is the speed of light, I'm going to get this equation right here. And if I try to make lambda subject formula, I'm going to get this equation right here. So that is all what this equation here is all about. So the idea is, if you're being asked to find wavelength and they said that the electron actually, there was an excitement, that the electron it was excited. So have it in mind that lambda is Hc all over En minus E naught, where this En minus E naught is the energy difference of that very particle. All right. So if E was given, if E is given already, so it means that I can write this formula that lambda is equal to Hc all over E. But where E is not given, but I know the En, I know the E naught, I can do their differences, their difference, anything I get that gives me the value of E, then I plug into this formula and solve for the wavelength. So you can solve for the wavelength, you can solve for the frequency, as the case may be. All right, so that was what was done, and we have an example as stated right on the screen. Now the question says an electron jumps from energy level to another in an atom radiating. Oh my God. An electron jumps from energy level to another in an atom radiating. I'm trying to see what was given there. Okay, but if I get this value here is our energy value. So it means that the energy difference has already been given as 4.5, radiating 4.5 times 10 to the minus 19 joules. All right, that's what we have there. So the energy radiation for that atom is given for that electron is 4.5 times 10 to the minus 19 joules, and they're asking us to find the wavelength. You see that? So clearly, I don't need to do much just to use this formula right here. So I know the energy, I know the speed of light, and I know the Planck's constant h. I'll simply multiply the speed of light by the Planck's constant and divide by E. And I told you that Planck's constant is value 6.6 times 10 to the minus 34 joules second. So don't forget that this is a value of your Planck's constant. All right. So once you multiply the Planck's constant by the speed of light and divide by the energy, that would give us the wavelength of that very particle. So you can try it out on your own. And if you do that, you'll get exactly the result. That is what that question demands. All right. So the next thing I want us to look at is electron spectra or emission spectra. All right. So basically, what do we mean by what do we mean by electron spectra? How many of you have heard electron spectra before? How many persons have heard about emission spectra or types of spectra, stuff like that, in your school or your personal study, as the case may be? Anyone? No one is saying anything. Do we take the silence to mean that you don't know what we are saying? Okay, now the idea is simple. Now, when we talk about emission spectra, just imagine, remember we talked about that atoms being heated, or they gain energy and they jump from one energy to another energy level. All right. So anytime atoms get energy, the energy can be due to heat, of course. So let's say the atom absorbs heat energy. Of course, they move from the ground state energy level down to another energy level. Do you understand that? So the excess energy in form of radiation emitted by a particle when the electron is returning from that excited state to the ground state, just like the atoms gets energy and jump from ground state to higher state, the atom can also lose energy and move from the excited state to the ground state. And of course, when the atom is moving from the excited state to the ground state, the energy, that very excess energy in the form of radiation that is being emitted by that particle when it drops from the excited state to the ground state is what we call spectra. So it can be called emission spectra, or it can be called spectra. All right. And we have various types of spectra. We have the emission spectra, we have the line spectra, we have the continuous spectra, we have the bond spectra, we have the absorption spectra. So all these things are the various types of spectra, and I wouldn't explain more than what you can see right here. So you can do well to read up and see their differences. I stated them for you just in case you're being asked to list the types of emissions, the type of spectra. Remember, spectra is just that energy, the excess energy that is being lost by the particle when it is moving from the higher state, from the excited state to the ground state. All right, that is what we call spectra. But take note, when the electron or when the particle is moving from the ground state to the excited state, it is called quantization. So take note. So you might be asked to state the difference between quantization and spectra. In quantization, the electron gains energy and then it's being moved from the ground state from one energy level to another energy level. It doesn't necessarily need to be the ground state, but the electron moves from one energy level to another energy level. That is called electron energy quantization. But then the particle can also lose energy and then drops from the higher excited state energy level down to the ground state energy level. And in doing that, energy is being lost. So the excess energy that is being lost is what we call spectra. And this spectra has various types, which are the emission spectra, line spectra, continuous spectra, the band spectra, and the absorption spectra. And that is what we have stated out in this very page. So you can do well to go through it and understand them for yourself. It's very important. Let's try to solve a problem right here. I don't know where this problem started from. Okay, we've done this one. We've done it. But there's a second example here. They said an electron. Let me still try to explain it. The solution is simple. Say an electron is excited. An electron is excited to an energy level E2. So you see, they gave us the energy level E2. And what's the energy level there? 2.42. Is that a minus? That's minus 2.42 times 10 to the minus 19 joules. So we have E2 is which is the excited state energy level, minus 2.42 times 10 to the minus 19 joules. All right. And they said to the ground state. So an electron excited to an energy level of E2 falls to the ground state. So E naught, which is the ground state energy level, is given as minus 221 minus 21.8 times 10 to the what minus 19 joules. All right, clearly you don't need to be told that your energy E is simply E2 minus E naught. All right, so E2 minus E naught will mean subtract this one from this one. And of double minus is going to give us a plus. So I'll be having minus 2.42 times 10 to the minus 19 plus 2.21.8 times 10 to the minus 19 joules. And anything you get here becomes the answer for your E naught as a case, for your E as the case may be. So the question says we should calculate the frequency and the wavelength of the wave. So how do I even find the frequency and the wavelength of this wave? Remember this formula from what we've done so far. from what we've done so far, remember we said that E is equals to what? HF, all right? If E is equals to HF, and I can find E by subtracting E2 minus E0. By doing E2 minus E0, I get my E. So it means that the frequency F is equals to E all over what? H, all right? So if I divide the E by the Planck's constant, I will get the frequency. And it's simple. Planck's constant is a constant and it's giving us 6.6 times 10 raised to power minus 34 joules, all right? So you put in that value, that gives you, divide the energy, which is already the difference between the E2 and the E0, divided by the Planck's constant, that will give us the frequency of that very wave. And they say we should find the frequency and the wavelength. So how do I find the wavelength? Wavelength is simple. Remember that V is equal to F lambda. And if I know the frequency, clearly I can find the wavelength, because the wavelength lambda is simply what? Dividing the V by the frequency. And of course, the V there is the what? Speed of light. So I'm going to use C as the speed of light, divide by the value of this frequency I obtained here. That would give me the wavelength of this very particle. So the solution is simple. So you can always try out these exercises, try them out on your own. Nothing difficult. I don't want to spend much time doing so many things. I want to believe that many of you go back to these videos, take your time, all right? So take your time, go through the videos, listen to the explanations, and try to do exactly the things I'm saying on your own. I may not be able to solve every question right here on the screen, but I say every details of what should be done, all right? So if you go back to the question, play the video over and over again, try to understand what is being said, and do exactly the same thing I say. You will get the value. All right. So ensure your values, every parameter is being computed rightly, just like your E is E2 minus E0 in this case. All right. So once you know your E, you know the Planck's constant, which does not change. Take note of it at H is 6.6 times 10 to the minus 34 joule second. So once you can always use, you know this, it means you can find the frequency. And having found the frequency, I can find the wavelength, because it is very easy. They ask us to calculate the energy of the photon. And photon talks about light. And the speed of light is 300 million meters per second. So our C is 300 million meters, which is 3 times 10 raised to 3 times 10 to the 8 meters per second. So if I find the frequency, I can now find the wavelength by simply dividing the speed of light by that frequency. Remember, the V is speed. And since the speed is out of a photon, it's going to be the value of the speed of light divided by the value of the frequency I got, and that would give me the wavelength and the frequency as the question implies. All right, so I think I'll be ending the class here, but I want you to ask me your question just in case you have any. I notice you guys don't do assignment. So if I give assignment, people don't attend to it. So I stop giving assignment. And then oftentimes I try to, when I speak, I ask questions, some of you don't respond. The last class we had, it was more like I was talking to myself all through, and it wasn't encouraging. So I feel we just talk like that, put down notes. If you think what we are doing is important, you go back and try to do things for yourself. And that is why if you observe the class take a kind of a different form today. So, but everything is well explained, and I want to believe you understand. So ask me your question just in case you have any. Okay, no question. So the attendance for this class, we have Matilda, we have Chris, we have Golden, we have Lucas. And 4 of you, I'll take your name on the attendance. In the absence of any question, now I will try to send an assignment to the platform, okay? So I'll try to send an assignment to the platform. You look at the question. It's more like a practice question, okay? So you try to do the question yourself, following what we've done in today's class. And I think that would help you, all right? So that is all I can say for now. And in absence of any question, we may just bring the class to a close. So see you guys in the next class. Have a good night rest.